Good afternoon, everyone. I am Pretom, presenting our research title as Pioneer, a physics-informed, constructive, and invariant framework for EV charging demand prediction. Over the next 10 minutes, I'll be explaining the problem we solved, how our system works, and what the result we have achieved so far. So let's begin. Let's start with the real-world motivation driving this research. As electric vehicle becoming the norm, driver constantly face the frustration of driving to a charging station only to find that it is completely occupied. Also, uncoordinated charging is triggering massive load surges. These surges edges the distribution transformer prematurely and threaten the stability of the grid. To manage this, the grid operator rely on accurate forecasting and demand dynamic pricing by raising the tariff during the peak hour to push driver to charge during off-peak times. But here is the critical gap in current research. First, they learn the wrong relationship between price and demand. When price goes up, the demand should goes down. That's the basic economics law. But in the data, high price appear during the peak hours when the demand is already high. So the model learned the opposite lesson. High price means high demand. That is superior correlation. Second, the model is trained in a central business district, fail in residential areas. It overfit to one environment and breaks in another. So no existing framework solve this both problem together. The Pioneer does. Next, this is our literature review. So no, the closest work to our is PEG, which is the physics informed meta learning, but it encodes only the discrete elasticity values and completely ignores the distribution shift across all environment. And other models are completely data driven model. They doesn't have the physics awareness in them. Next. So about our objective. Our objective is to build a framework that is physics consistent and environment reversed, and also should be model independent. And these are the three properties that no prior work have achieved together. The fundamental objective was first to develop an physics info and constructive invariant framework using hybrid GNN and TCN based forecasting model. Then to introduce a novel independent pre-training and fine-tuning stage that can induce physical law and environment invariancy. Third, to validate this result with existing baseline models like VAR, LSTM, GCN, GAT, and STGCN, and also the PAC. And lastly, the performance evaluation of Pioneer in different forecasting horizons. So we have found the two core challenges. First of all, the physics violation. So data shows the price and occupancy moves together. The model runs this wrong direction. The correct direction is the when price goes up, demand should goes down. And challenge two is regional heterogeneity. CBT zones behaves very differently from the residential zones, but a model that performs well in average can silently fail in a specific horizon or environment. The next slide is about the methodology. So Pioneer treat the city as a graph, each node a traffic zone. So, and the dataset we have used covered 247 traffic zones in Shenzhen, China, covering 18,061 charging pile sampled every 5 minutes over a month. And the special module is graph attention GET. Instead of treating all neighbors equally, GET learns which neighboring zones matter most. The busy commercial zones get higher attention than the quiet side state. We expect multiple GET layers so information can travel across multiple hops. Because a price change 2 zones away still influence me. And then also there is an effect called spillover. So our special model also capture the spillover effect. When one zone fills up, the drivers reroute to the nearby zones. So this is called the spillover effect. Next slide is the upper one is the stage one, the pre-training stage, the constructive physics learning. This is where we teach the model the law of demand before we see the real data. We create two types of example. First of all, the physics constant pair. where the price rises and demand falls. This is correct one. And the physics valuing pair, where price demand rises with price or stays flat or collapse unrealistically. These are wrong. The model tend to pull toward the correct pairs and push away the wrong one. This is called the physics info ancient objective. We use no rigid equation, just learning from the example. Bottom of the step 1, there is SS2. The step 2 is the invariant risk minimization or IRM. We divide the zones into 4 environments based on the zone type and the pricing policy. CVT fixed price, CVT dynamic price, CVT non-CVT fixed price, and non-CVT dynamic price. We added a penalty that punishes uneven performance across all 4 groups. This informed the model to learn the pattern that works everywhere. Then this stages passes the data to our physics TCM block. This is a temporal module. And instead of LSTM, we use physics TCM because it is causal by default. And causal means the model only looks the past, no future data is leaked in the process. And in the temporal module, we use 4 time scale: 10 minutes for immediate price response, 20 minutes for special spillover, 40 minutes for building peak, and 80 minutes for full rush hour cycle. Next, in the next slide, this is our full Pioneer architecture altogether. On the left, you can see the 2D convolution fuses occupancy and price, then gate layer handles a spatial relationship, then the physics TCM captures the temporal pattern at 4 time scale, as I mentioned before. Then comes on the right side, you can see the stage 1, the CPL patterning that injects physics. Then comes the stage 2, that the fine tuning stage that enforces cross environment robustness. Next slide. In the next class, we will be discussing about the result. There are the main result. At 50-minute horizon, which is the most critical horizon for real-time management, Pioneer achieved the lowest RMSE of 2.89 and the lowest MEE of 1.36 across all models. So compared with the PAG, which is the best physics-informed baseline, Pioneer improves average RMSE from 5.50 to 4.71 and average RE from 19.96 to 17.95. In the bottom of the result, we can see the heat map, which shows the percentage of improvement from the baseline at 30-minute horizon. Against the purely data-driven models, our model gains 40 to 70% improvement, and against PAC, the improvement is 16.5 to 31.9 in MEE and RMSE. Next. So about the model independency. A key feature of our research was that the CPL and IRM should be model independent. So you can plug them into any other neural network backbone. We tested this on GCN and LSTM. For GCN, adding CPL and IRM reduced the average RMSE from 10.30 to 9.01. That's a clear improvement. But for LSTM, the gain is small. Why? Because CPL generate a spatially propagated physics signal, and LSTM process each zone independently in time. So it cannot use the spatially slower part of the CPL. So, and on the other side, GCN being a spatial aware model, it can use the full signal. So the final verdict is, the more spatially expensive the backbone is, the more it benefits from CPL. In the right side, you can see the ablation study that confirms that each component that contributes. CPL alone helps, IRM alone helps, but both together gives the best result. Next. To conclude, Pioneer solves 2 more problems that no prior work has solved together: the physics inconsistency and the superior correlation of price demand correlation, and lastly, the poor generalization across heterogeneous city environments. We achieve this by 3 contributions: CPL, which teaches price elasticity by example; the IRM, which enforces equal performance; and the physics TCN that schedules map directly into 4 identifiable EV demand timescales. About the future work, our future work include adding weather and traffic data, probabilistic uncertainty estimation, and post-city validation on different datasets. Lastly, I want to thank you for your time and welcome your questions. Thank you.